Let's take a look at the electrostatic energy that develops when we bring together a continuous charge distribution. Just to review, when we had discrete charges, suppose we have n of these things, the work done to assemble those n charges, which we call Wn charges, is equal to 1/2 times the sum from I equal 1 to n of the charge q sub I times the potential at the position of q sub I. And so that's V total R sub I. By total we mean the potential due to all the other charges. You recall we derived this by just considering a finite number of, say, 4 charges. The important thing to remember was that, for example, to bring in the last charge, we have to have the relative distances to all of the other charges. Although I didn't write it, this would be funny R14. And so that's what you need to get the potential. Then once you have the potential at Q4, then the contribution to the work, 1/2 times this charge times the potential at this point. I've just repeated that up here for n charges. Let's consider a continuous charge distribution, so we'll call that rho, and that's at some position r. And we're going to construct small cubes of charge. Let's call those delta q sub I. And that will be the charge density times the volume. We'll use delta tau sub I. So we'll write out the work for n charges as if these were n of these little cubes. So that's equal to the delta q sub I times the potential at R sub I. So just rewriting that, we'll swap these two elements here. So we have the charge density times the potential times our little volume element. So let's let n go to infinity. These would tend to go to 0. Then our sum will go over to an integral. We end up then, for the total work to assemble all this charge, is 1/2 times this integral right here. And that's a very fundamental relationship. Repeated that up here. So now we'd like to develop another expression. I'm just going to drop the argument r to save writing. Let's start with the divergence of E times V. That's equal to the divergence of E times V, and then E times the gradient of V. The del operator distributes. We take this and solve it for this term right here, so we'll have this term minus this term. So that's what I have here. We're going to replace the gradient, so actually minus del V. Here's our minus sign, here's our del V. We'll replace that with E. Remember that the divergence of V is the charge density over epsilon naught. We're going to multiply by epsilon 2. So I've done several things here. I've replaced this with E. I have changed del dot E to this dependence on rho, and then multiplied by epsilon 0 over 2. So if we do all that, the divergence of E term gives us this. The second term gives us this, and then the third term with a plus sign gives us this. So now we'll integrate every term with respect to volume over some volume tau. The first term looks like 1/2 times this integral here, and then I can factor out an epsilon 0 over 2, and I have these two integrals. So it's this one right here. The integral of this up here is this. And then here's the integral of the last term right here. Let's take a look at this term here. It's a divergence of some function here, a vector. So we can convert that to a surface integral using the divergence theorem. I've done that right here. So you take the vector itself and you dot it into a surface element and integrate over the surface. What surface? Well, it's the surface that encloses the volume tau. Rewriting then, we'll have our left-hand side being this quantity here, and then we have epsilon 0 over 2 times these two integrals right here. So I've repeated that up here, and the first thing to realize is this is what we just derived for the work to assemble this charge density. All the charge that goes into this would give us the work done to assemble this. Now this is misleading. What I mean by this is that suppose we have this blob of charge. This is rho of r inside this volume here. To assemble all of this charge is what we're talking about here. Now the right hand side, we have this rho of r, and I've drawn it over a finite volume here, It could actually extend over some small region, or it could be very large. But we can always make tau, the volume, and therefore this surface S, much larger. So if you tell me this is the size of the United States, then I'll make my tau the Earth, or something like that. You can always go bigger than where you have charge. You can't have charge go to infinity because that would be an infinite amount of charge. That's one way to look at it. As these get really big, so we're making this volume and the surface that contains the volume very, very large, then notice that as we get far away from that charge, we'll have a 1 over r dependence on the potential. We'll have a 1 over r squared for the E field, and the surface, let's say it's a sphere, goes as r squared. So basically what we're saying is we're far enough away so that the charge starts to look like a point charge. So if we go back to our integral then and multiply v times e times s, which would be the units and the magnitude of this, this goes as 1 over r. Now remember, you're only evaluating this on the surface. This quantity here tells you how this surface integral goes. It doesn't matter what this is inside of the surface, because we only care about what this is on the surface S. What the final result is that if we make this very large, this whole integral goes to 0. So what we're saying in this expression here, we're going to drop this term. What about this one? Remember that this here is evaluated all through the volume. So if you had, for example, a region of very intense E and then it falls with R, you still get a value for this integral no matter how big tau is. And the reason is you are evaluating this argument E dot E throughout the volume tau. This is the only term that survives. It's not 0. The work to assemble this charge is equal to this quantity right here. So it depends on the E field that results when you're finished and the volume integral of that E field. Here's the thing, rho generates E, but if E exists, it has energy. This is the work we did to assemble that charge, and then the resulting E field, that if we integrate it, multiply by the front end here, and square E, then we'll get the same thing. We say then that the E field that is generated has energy. It's equal to this quantity here, and so we sometimes call it capital U electrostatics, or capital U with a subscript E. If you look at the argument here, so put this inside, so epsilon 0 over 2, that is giving you a function, if we integrate it over tau, gives us the energy. So that's like an energy density. We define this quantity here as the electrostatic energy density of the E field, and that's what we call little u sub E. We integrate u sub E over the volume, then we get the electrostatic capital U, and of course just plugging it in again we get this quantity here. I would memorize this quantity here and realize that if we integrate it over the volume, then we will get the total electrostatic energy. So again, a very useful relationship. If we repeat then that we have these equations that we just derived, we can go back to the total energy to assemble all the charge, which was equal to this quantity here. Because the work done to assemble is equal to the energy that we end up with, we can equate this to u sub E. So the energy can be thought of as stored in the assembled charge, or we can think of it in terms of the resulting E field having energy. Either is correct. You'll get the same answer if you use one or the other. Here's the deal. If you have this charge, let's just represent it again by some finite extent. And so this is rho throughout this. Doesn't have to be constant. If you were to let this charge go, what would happen is that you would end up with kinetic energy of all these little charge elements at infinity. And that would be the total energy that you have when you assembled the charge. On the other hand, if you hold this charge, then the E field that exists inside and out, if we integrate that, which is up here, so we integrate over that field, then we get the electrostatic energy that results. Well, let's do a simple example, and that is find the energy due to a uniformly charged sphere, total charge Q, and radius r. So we have this shell of charge. It's a radius r, and the total charge on that shell is Q. Well, how did we make it? We brought little differentials of Q's to the sphere and distributed them so that we had a uniform charge density on that surface. If it's distributed uniformly, then the charge density at any point on the sphere is just the charge Q divided by the area of the sphere. Now we know that the potential of a spherical charge distribution can be written as K over Q divided by R. This would give us the potential right on the surface of the sphere. We know that if we do a shell of charge, then anywhere out here, including right at the surface, it looks like a point charge at the center. And so that gives you this potential. We put that into our equation, and we're just going to equate it to U sub E. So we have 1/2 rho capital V d tau, which goes over to a surface integral, 1/2 sigma times V integrated over the surface. Realize that this step here is just what we did when we found, for example, the E field or the potential due to surface versus volume charge densities. We put in our rho. This is rho right here. This is our potential on the surface, and then we integrate over the surface. Well, you can see that all of this is a constant, so we can bring that outside. I've done that here, so I have kq squared 2 times the area times r in the denominator. Then we just have the integral over the surface, and that's 4 pi r squared. And this is the resulting energy required to assemble that charge, and we equate it to the energy of the electrostatic field that would result. Let's do this problem a different way, and this of course is using the E field. Now remember that if you have a spherical distribution of charge, if you're outside of that charge, so if you're out here at some value little r, then you can think of the E field as being generated by a point charge of magnitude Q right at the origin because of this spherical symmetry. This is what the E field looks like, the point charge equation. This is the magnitude of E, which is right here. We square it, and so we get E squared. Now remember that the total U sub E is going to involve the volume integral of E squared. We have epsilon 0 over 2 times the volume integral of E squared. We put in our E squared, and then we have to put our d tau. Well, because of the spherical symmetry, we use spherical coordinates, and this right here is the d tau. And notice that it has 3 d's because it's a volume expression you'll find in all the E&M books. Simplify what we have here then. We have k squared q squared. The 2 pi comes from the integral over phi. The 2 comes from the integral of sine theta d theta. And remember, the range for theta is 0 to pi. The range for phi is 0 to 2 pi, and that's why we get 2 pi, and this involves the integral of sine theta. The integral from capital R to infinity so that we get the total field. Doing that integral, we end up with this expression here, and so we have the same result that we had when we integrated the rho times V over the charge distribution. So we get the same results for both of those techniques. Now there's a problem. I just want to point this out because it does have importance in terms of understanding fields. This is the expression that we used. We are talking about the density of energy in the electric field. Because of the square of E, this will always be greater than 0. If we look at the discrete charges, where we have q sub i's and q sub j's, let's take the potential and write it in terms of q sub j, then you'll notice that you have products of qi, qj, and it's possible that you could have a positive value or you could have a negative value, depending on the 2 charges that you're putting together. This will only occur with point charges. And so if you look at the Q1 equal to Q and Q2 is equal to minus Q, then for just two charges we would get a negative result. And in this case we would have attractive charges. These equations, where we have for n charges, we have this result for discrete charges, and this one for assembling all of the charge, which is equal to this quantity here, so continuous. These are different in a major way. In the first case, all the charges are already made and then assembled. In 2, we start from scratch and build up all of the charge. So if we apply 2 to 1, so in other words we try to consider assembling a charge density that was of discrete charge, we would end up including what we would call the self-energy of each charge, because we haven't made those charges. The self-energy of a point charge, if you remember, is infinity. And the reason is you're putting a charge Q at a point. There's no radius. One can play around with integrating this in terms of the work done to create one charge, and that's equal to this quantity here, and we get infinity. If we use this equation right here, we have to avoid point charges inside the volume, because you would have infinities in E, and so therefore you would get an infinite amount of work, and just because the energy of a point charge is infinite. For a continuous distribution, if you looked at this rho in the volume d tau at the point P, then as you let the volume go to 0, you end up getting 0. So it's as if you consider your rho in this region here. If you don't look too closely, you see some charge in a little volume here. But as you let that volume shrink, you could think of it this way, that if you get too small, then these things look discrete, and you're looking in between. So you don't have any charge density if you go small enough. Well, the consequences are that we do have a way out, and for discrete charges we can ignore this equation. So we ignore this idea of a field energy density, and we just think of W as equal to what we derived here as being the potential energy of the whole system. And what that means is that if we let go of all these charges, you will get this much kinetic energy of all the moving Q sub i's at infinity. If we make these charges, so we have all these charges, and so 1, 2, 3, 4, 5, 6, 7, so n equals 7, they're in these positions, and we did this much work to get them there. If we let go and let them go to infinity, we will get kinetic energies of all these particles summing up to W. So we can think of that as a energy either of assembly or kinetic energy if we let go. What we're doing is we're just not worrying about the E field that would be in between all of these charges. We're only thinking about in terms of energy that we make or acquire if we let go. On the other hand, if we have continuous charge densities, there are no self-energies to worry about, so we can write down that the work to assemble is equal to this. That's equal to U electrostatic, which is equal to this. So we use either one, we get the same answer. Both will give the same result and will be consistent with a E field energy density equal to this quantity here. Remember that this is a local quantity. It's evaluated at a point, so the energy density is at a point. If we integrate over all space, in both cases we'll end up with the work done to assemble all the charge, which is this quantity here. We'll end up with the total energy of the electrostatic field, which is this quantity here. And by integrating over all space, we get the total, which is U electrostatic.